Okay, so let's get started. As most of you know, the homework is due today. We've also posted a new homework assignment, so that will be due next Thursday. Luckily, Al was nice to you guys this time, and I think it's going to be not too bad. That's what he says. So, not too bad means pretty damn hard on his scale, I think. Anyhow, sorry to give you guys homework during Thanksgiving. But it will be due Thursday, so you will have time to work on it next week, and there will be office hours next week, so you can ask questions. Okay, any general comments before we start today's lecture? Comments about the projects, things like that? Okay, so let's pick up where we left off. Let me step back a little bit and review what we've done so far. So the first lecture on oscillators, we looked at the feedback approach of analyzing oscillators, positive feedback, loop gain. Last lecture, we looked at the negative resistance perspective, that if we have a lossy LC tank, our active device is in effect a negative conductance that exactly compensates for this loss. And in fact, what we did was we showed that the oscillator, for instance, the negative resistance oscillator like this, we just take a transformer at the output, an inverting transformer, hook it up back into the input. If we actually probe the circuit with a test source Vx and look at the current Ix, what we find is that Ix is actually negative. In other words, the input impedance here, or let's say the input conductance, Gx, is minus the Gm of the transistor divided by N. Okay? And we showed also that this perspective for this particular oscillator is equivalent to the loop gain perspective, because to make this resistance larger than the lost tank, that requires Gx to be larger than, let's say, Gt, which is equivalent to Gm R tank over N greater than 1. All right. Now, there are particular oscillators that, let's look at, for instance, the Colpitts oscillator. So the way we analyze the Colpitts oscillator last lecture is we noted that it's a common base oscillator, and therefore, to apply positive feedback, you can use a cap divider because you don't need any inversion. And so the question is, from a negative resistance perspective, that means that if I look into these terminals here, if I calculate this current, that should correspond to a negative resistance. Okay, so let me do that. So the current Ix has two components. It has a component which is this transistor current. Let's call this Gm V1, where V1 is this voltage, plus basically the current flowing into this capacitor. Let's call that Vx minus V1, let's say, so plus V1, times j omega C1, right? Well, what's V1? V1 is this voltage, and if we assume that the current, basically in resonance, that most of the current is flowing through this capacitor, in other words, the transistor contribution is small, we can assume that basically, in other words, if we neglect the loading here, then the voltage V1 is basically minus the voltage Vx times the divider C1 over C1 plus C2. Okay. And if I substitute here in this above equation, if I substitute for V1, I have Ix is minus Gm C1 over C1 plus C2 plus basically 1 minus this, so 1 minus C1 over C1 plus C2 Vx j omega C1. And this simplifies to minus, so this is also times Vx, minus Gm C1 C1 plus C2 Vx plus C2 over C1 plus C2 j omega C1 Vx. Okay. Also, another observation here is that this transistor has some capacitance that's going to affect these calculations. In particular, it has C mu, but C mu just looks like a capacitor in parallel with our load, right? So I can just neglect C mu and put it in shunt. That's negligible. The other capacitor is C pi, and C pi can just get absorbed into C2. So really I could say C2 is equal to C2 prime plus C pi. Okay? And then I can just assume this transistor doesn't have any capacitor parasitics. All right? Questions? Okay, so we simplify this equation. Basically, let me just look at this assumption that I make. I'm assuming that the transfer function from V1 to Vx, I can actually analyze this exactly. The transfer function exactly is j omega c1 divided by j omega c1 plus c2 plus gm plus g pi. Okay? And so you can see now is the assumption is that this term is much greater than gm plus g pi, right? And that's when we get this approximation. In other words, 1 over n. Okay? So if it's actually very important that this approximation hold, because you can see when this term dominates, this thing becomes real. In other words, the voltage feedback is actually real. If this term is important, then the voltage feedback is not purely real and there's a phase shift. And as you'll recall from the first couple lectures, if there's a phase shift in the feedback network, then the circuit will not oscillate at resonance. It'll oscillate off resonance in order to compensate for this phase shift. Okay? So if we just now go ahead and substitute from up here, if we've done everything correctly, the answer is that I have basically a real resistance, which is Gm over N. This is Gm, this is N, basically. And I have a imaginary component, which you'll observe is just a series combination of C1 and C2. Okay? So in other words, the input impedance looking into here is, let's say the input, admittance is j omega c mu, right? Plus this in series with this, plus a negative resistance, which we find to be minus Gm over N. Okay? Any questions? Okay. So now it's very clear how we would design this Colpitts oscillator based on these equations. Let's say I bias this up. I can now use my inductor to supply to tune out basically C mu. So this is a bypass capacitor. This inductor is tuning out C mu. It's tuning out this in series with this, where this includes the transistor parasitics. And it turns out that this is a really nice oscillator. You can make it work at really high frequencies. You can see that if you do a more complete analysis and include this phase shift, you'll find that at very high frequencies it begins to suffer due to excess phase. Let's call this excess phase. But for a very fast process where your FT is, let's say, at least a factor of 10 bigger than the oscillation frequency, this works pretty well. Okay. All right. Well, the same kind of analysis can be applied to the Clapp oscillator. So the Clapp oscillator actually, in some ways, is kind of mysterious, right? So if I look at this circuit, it's not very obvious where the loop is, right, and what the loop gain is. If you follow the procedure that we used last lecture, you can exactly calculate all the parameters for the circuit, the loop gain, and predict the oscillation amplitude. But using the negative resistance approach, it's actually quite simple. If I dump a current onto this capacitor divider, the action of the transistor current will produce a negative resistance. And the way to see that is actually, well, let's just do the calculation. So here, V pi for the transistor is approximately this current flowing through C1. So it's Ix times the impedance of this capacitor. Again, we're assuming, implicitly, we're assuming that this circuit is going to be embedded in a tank, and so that the tank current will dominate. Okay, keep that in mind. So we're neglecting the base current that flows from here. And that means that Vx is just V pi plus this voltage drop, which is the transistor current, IC, plus Ix flowing into ZC2. Okay? In other words, that the voltage Vx is, substituting now, I have Ix ZC1 plus IC plus Ix ZC2, or Ix ZC1 plus ZC2 plus IC times ZC2, but IC is nothing but the GM of the transistor times V pi, which is GM Ix ZC1. So in other words, Vx is Ix ZC1 plus ZC2 plus GM ZC1 ZC2. Okay. Now if you go back to your analysis of LNAs, you might find this, that we didn't even have to do this, because remember, we found that if you put a degeneration inductance, the input resistance would have a real part. If I degenerate with a capacitance, right, I can absorb C1 into C pi, and then C2 just looks like capacitive degeneration. That should produce a negative input resistance. And you can see here, when I multiply 1 over j omega C1 and 1 over j omega C2, I get a negative real part. So Zx, which is the ratio of Vx over Ix, looks like basically two capacitors in series plus Gm j omega C1 times j omega C2. In other words, Rx, which is the real part of this, is minus Gm omega squared C1 C2. Okay, questions? It's interesting to see that there's a frequency dependence in this negative resistance. In other words, as we go to higher and higher frequencies, we get less and less negative resistance. And so this naturally tells us that this oscillator has some frequency limitation. You can't arbitrarily create a negative resistance. Okay? Now in practice, what we want is that Rx should be bigger than Rs, where Rs is the series resistance that we hook up. So here's Rs, here's the tank resistant inductance, let's say L tank, and we're going to hook this up as follows. So this, looking into here, Rx should be bigger than Rs for startup, and LT should resonate with this series combination. Okay. Now again, just as before, you can include C mu later. It's pretty trivial to include C mu in the calculation. And as before, C pi gets absorbed into C1. So now, replacing here, we see that Rx bigger than Rs implies that Gm has to be bigger than omega squared C1 C2 times Rs. Which tells you that as you go to higher frequencies, you have to pump more current in your device to meet the oscillator startup conditions. Okay? Now you might think, well, I can just reduce, basically Rs I can't do much about, right? That's fixed by the Q of the inductor. But I could always use smaller and smaller capacitors, right? But in the limit, you're going to hit the capacitors of your actual device. And typically, you don't want these capacitors to be on the same order of magnitude as the parasitic capacitors, because the parasitic capacitors vary over process and temperature. So you want C1, C2 to be on the order of, let's say, just arbitrarily, 10x C parasitic, so that you have good process control. Okay. Now, based on this simple analysis, we could also predict the oscillation amplitude, because if I just redo this analysis and instead of using little gm, I use capital GM, or the large signal GM, then I have an equivalent condition that in steady state, the large signal GM would be identically equal to omega squared C1, C2 Rs. Okay? And if this were a bipolar transistor, I know that the large signal GM is basically given by these modified Bessel functions times the small signal GM, and basically the small signal, so here I can solve for B, which is equal to V pi normalized to KT over Q. So I can solve for B, and once I know B, I know the oscillation amplitude. Okay? And notice, the moment I use these equations, I'm assuming that there's a current limiting mechanism. And here the natural current limiting mechanism would just be to bias this up with a current source. Okay? Or a large resistor. All right, so last lecture we also talked about how the same analysis can be applied to any kind of Moss oscillator, right? This is the same Colpitts oscillator. Can we zoom in on this? Thank you. So this is again the same Colpitts oscillator we just looked at. This is the floating version, and then we can ground different points. I can ground the drain, and or I can ground the emitter, and I have a Pierce oscillator, a Clap oscillator. And we also talked about last lecture that technically these oscillators have caps in shunt here, if we just go directly from here to here. But there's no need to have this extra capacitor. We can actually eliminate it and form resonant tanks as follows. So this is the resonant tank here. This is the resonant tank here. Okay. All right. Well, let's talk now about differential oscillators. So let me build this up a little bit differently. Let me just take a two-stage amplifier, and let me take a broadband two-stage amplifier. So one nice broadband two-stage amplifier is a diff pair if I run it single-ended. In other words, I'm going to ground this side. I'm going to have a follower driving a common gate amplifier. And very early in this class, we learned that this is a very nice broadband amplifier. It's broadband because the follower stage is very broadband, and this stage is driven by low source impedance because of the 1/GM impedance seen looking back. So this is a two-stage amplifier, and in fact the gain from here to here is positive. So I can just take this point, feed it back, and hook it up back into the input. And I have positive feedback. And the loop gain is very easy to calculate. Let's call this M1, M2. Basically, the loop gain is going to be, if I assume this is a perfect follower, it's going to be GM2, let's say RT here. Remember, I'm going to make a tune network, so this is LT, RT. So at resonance, it's going to be GM2 RT divided by N. So again, the same equations apply that we studied before. Yes?
So what's the difference between adding a transformer and adding the two caps? I mean, I assume that this is to do with the phase shifting, right?
Yeah, in this case, we can use a capacitor or a transformer. Both would work. Yeah. If we use the transformer, we wouldn't need to invert. We just use basically straightforward. And we'll look at that in a couple slides. We'll come back to that. Okay, so this is very straightforward, right? Well, if you stare at this a little bit, you say, well, you know, why use a single-ended signal? Why not actually feed back a differential signal? I'm kind of wasting the other side of this tank. I could also take the output here and feed it back here, right? So let's do that. So what I can do is I can have two tanks. Connect this to VDD. And I can have my diff pair as before. This is a virtual ground for differential excitation. And so now I can take this side and this side and feed this back over here and feed this guy back over here. Okay? So this is a fully differential version. Okay? So what's the benefit to doing that? Well, look at what happens to a loop gain. If now this device is not acting like a follower, it's acting like a GM stage. So the loop gain is GM1, right? This is a virtual ground, times this R tank divided by N. That gets applied here, multiplied by GM2, R tank, and then also divided by M, and the signal comes back. In other words, the loop gain is GM-RT over N squared. So that's the benefit to using a differential circuit. The other big benefit of going differential, you might argue, well, for the same current, this GM is actually reduced, right? So it's GM over 2. The other advantage of going differential is basically common mode rejection. So if this is perfectly a differential circuit, any disturbance on the supply will not affect the circuit. Likewise, any disturbance on the ground will not affect the circuit. These signals are common mode, and if this is perfectly symmetric, it will not respond to common mode signals. So this is actually one of the biggest benefits. And the reason this is really important is that once this thing is oscillating, the actual closed loop gain is nearly infinite, right? We saw that. As the loop gain approaches 1, the closed loop gain goes to infinity because we have positive feedback. And as we'll see next lecture, it's actually not infinite gain, but it's a very high value of gain. So this is a positive feedback amplifier with loss of gain. That's a simplified way of looking at it. So any noise signals that are near the center frequency of the tank will actually influence the tank in a substantial way. And that's a really bad thing. So we don't want any disturbances near the center frequency to influence this oscillator. We won't talk about it in this class, but in fact, this is a nonlinear system, and there's a concept called injection locking. And you may have heard about it. It's also called mode locking. The idea is that if there's another signal that comes in that's close to the frequency of this guy, if, crudely speaking, there's more energy in that signal than there is kind of noise in this circuit will lock to that incoming signal. So what you can have is that, let's say that this is a disturbance, basically an unwanted signal, that locks our VCO. That's a really bad thing. You know, we're designing a VCO here to set up a reference for, let's say, our mixer. We want the frequency to be well defined. We don't want it to be influenced by other signals. And that's why going differential is so important. Okay, another nice thing about going differential is we have a high differential swing. Okay, and we'll realize later on that maximizing this voltage swing across here really helps with the phase noise. So a very simple way to look at it is that there is some noise in this circuit, and there's basically your signal, and you want to maximize the ratio of your signal to the noise in the system. And as we'll see, basically what you do is you generally will increase the current up to a point where you maximize this amplitude, and going any further than that current won't actually help you because it just will increase noise without increasing the amplitude. Okay, so we'll talk about that later, just a preview. Also notice that in this circuit, if I want to maximize the loop gain and minimize the current consumption, I should really set this feedback factor to 1, right? Because I'm losing gain by having a feedback factor. So if I just set that feedback factor to 1, that would be equivalent to basically eliminating this capacitor, right? But the DC level here is very compatible with the DC level here. So what I can do is actually directly connect these 2 points. I don't even need to use a capacitor. So the idea is now have my inductors, and I can just take these signals directly and connect them, and I would also connect a capacitor across here to resonate with this inductor. And basically here, to make an LC tank, I forgot to put in my caps. So let me step back and put in my caps. So here this is a single-ended version. Now I have 2 caps, and because this is a differential signal, I can actually make my cap smaller by connecting it across here, right? Because these voltages are out of phase. So the cap looks twice as big. So instead of putting 2 caps here, I just put 1 cap across here, and it resonates at the right frequency. Okay. Now most people draw this circuit in a slightly different way. They draw it in the following way. And it's exactly the same circuit, right? I've just flipped things around. And in fact, there's no reason to use 2 inductors. You could just use 1 inductor and connect VDD at the center point. And so this is an even more differential version of the circuit. This center tapped inductor sometimes called the differential inductor, basically should be a symmetric structure. So what do I mean by that? Okay, let me stop here and take some questions. Okay, what I mean is that I want to preserve symmetry in this circuit because symmetry helps me reject any kind of common mode signal. So if this inductor is off chip, let's say it's some kind of coil wound like this, and I tap the center, that's right, that's great. There's no problem there, right? The circuit looks very symmetric. But if I build this inductor on chip, it's probably going to be a spiral, so it might look something like this. Okay? So there's a couple of problems here. First of all, where's the center of the structure? Where do I tap it? Okay? So let's say that you, by trial and error, find the right point to tap. So this is the center. This is the electric center. It's basically not the geometric center of the structure, right? It's the electric center because we want the inductance to be half. So half the inductance, if you look at this as 2 inductors in series which are mutually coupled, then this path, looking in from this path, I should see the same inductance as I do from this path, right? That way this point will be a virtual ground. If I actually choose the wrong point, then I won't have a virtual ground and I'll actually end up dissipating power into that node. And we'll see that's a big disadvantage. Okay? So this layout is actually not so good. One way to make this layout more symmetric is actually just take 2 inductors, let's say like this, and connect them like this. Okay? Yes, Firas.
So the resonant frequency is the one determined by LC or L over 2C?
Yeah, it's L and C together, yeah.
Like the complete L, right?
Yeah. Exactly, yeah. So you can think about it, I'm going to put a capacitance in parallel with this, and that's going to resonate with this total inductance. Okay? So this is one approach. This is now, at least it's symmetric. But what you see here now, because these two coils are far apart, this M factor is small, the mutual inductance. And so to get the same value of inductance here, if you think about what's the total inductance of this guy, if I put a current in here, the inductance is going to be L1 plus L2 plus 2 times M, because they're mutually coupled. So I pick up an M when I go through this winding, and when I go through this winding, I pick up another M. Assuming the currents are the same, they just add and give me 2M, right? And if these are basically the same value, I get 2L plus M. And M basically is geometric mean of L1, L2 times the coupling factor. And if they're equal, this gives me 2L1 plus K. Right? So let's say on chip, typical coupling factor is about, for this kind of structure, 0.7. So this inductance is actually pretty nice. It's going to be, there's a 70% boost due to the mutual coupling. If I do it this way, and K is practically 0, maybe it's 1%, there's only a 1% increase in the inductance, so practically nil. So I have to actually make these windings much bigger to get the same value of inductance. And because the bigger you make these windings, the more they couple to the substrate, they're going to actually have lower Q values. So this is due to substrate coupling. Okay? Questions? So basically, I'd like to get back to something like this, but something that's more symmetric. And one way you can do that is with a symmetric layout. So let's say a symmetric inductor layout. And here's one way to do it. You guys can dream up other ways to do it. You basically come in so this is terminal 1, this is terminal 2, and this is the center. And so you can see that kind of the geometric center is also the inductance center and the resistance center, and basically you are benefiting from the mutual inductance between the different turns, right? So let me just sketch what the first turn looks like. The first turn does something like this. And then goes to the center. So this is 1, this is the center. And if I reflect this about the center, then that's the second terminal, that's the second winding that comes into here. Okay? So this is a nice way of doing the layout. Remember, this is the inductor that we're designing. So it's this inductor with the center tap connection, and then I put my cap across here. Okay? Questions? Okay, well, another nice trick is to take to reuse some current, and let me give you kind of an intuitive way of seeing how this comes about. Let's go back to this amplifier and interpret it in another way. Let's say that I have an amplifier like this, and I have another amplifier. So this is an inverting amplifier stage. This is another inverting amplifier stage. And if I just connect them together, I get a feedback system, right? And this is essentially the cross-coupled pair that we just drew, right? So this is another way of looking at things. Well, what's another inverting amplifier? Well, I could also use something like a CMOS amplifier. The nice thing about a CMOS amplifier is that it's also inverting, but as you guys saw in the first midterm, the GM of this guy adds to the GM of this guy. So it's like having two transistors in parallel, but sharing the same current. So that means that for a given current budget, I can get more loop gain out of this, or vice versa. For a fixed loop gain, I can get less current. So again, I drive a tank with this. I have to make sure that I don't mess up the DC here, but for AC circuit, let me just draw it like this. And I'm going to take this output, connect it back into the input, and this output to the input of this stage, right? So what does this look like? Well, I'm going to redraw it like this, just like I redrew the other amplifier. And actually, this is optional. We'll see that later. So if you don't like this, just ground it so that you get the same exact circuit. And then, of course, you have the LC tanks here and here. And then, just like before, there's no reason to have two LC tanks to ground, especially because this ground node would interfere with the bias point here. It's much better just to connect the LC tank across. So finally, draw a quick version of this. I have my LC tank, I have my transistors cross-coupled, and let's say connected to ground. Okay. Okay, now, so our perspective has been more in terms of amplifiers and getting positive feedback, but we know that this is equivalent to negative resistance. So let's explore the negative resistance perspective. So you can do it either with a current source or a voltage source. But it's fundamentally a differential circuit. So I'm going to apply a differential voltage here, Vx, and measure the differential current, Ix. Okay, let's call this M1, M2, and this is the NMOS version. Equivalently, I can analyze the PMOS version. Well, you can see this is actually a very simple circuit. The negative conductance connected across here, if I neglect the capacitances in this device, the current flowing through this device is just the GM of the transistor times half of Vx, because it's a differential circuit. So Vx gets applied across M1, M2 in series, and so half of it applies here, half of it applies here. The VGS of this device, therefore, is Vx over 2, and the current is Gm. So the net result is that because this guy is connected to the negative terminal, its current actually flows in the other direction, and the net result is that we get a negative resistance. Okay? Now, when we actually build these circuits, what we have to be really careful of is two things. So for differential oscillators, we want to preserve the symmetry. As we saw, we can use center tap inductors to do that. We also want to, let's say, exploit the virtual ground. Okay? And let's see how that comes about. So here we connect this center tapped inductor, and we put a capacitor here, and then we have our transistors again. Getting lazy today, so I'll draw my transistors like that. Well, it turns out that it's pretty hard to build a symmetric capacitor like this. Most processes, the capacitors you have in most processes are not symmetric. There's basically one version where you have a top plate, a bottom plate, and a very thin oxide. And so this is your top plate, this is your bottom plate. Well, of course, this sits right on top of the substrate, so there's the bottom plate parasitics. And that, first of all, if I put this in here, you'd see that it would add an additional capacitance to one side. That's not nice. So what you would do is maybe you'd put a compensating capacitor on the other side. But unfortunately, it's also a lossy capacitor because this substrate is conductive. You could try to shield it. You could put actually a conductor under it to get rid of the substrate resistance, but then the bottom plate parasitics would go up even further, and so the asymmetry would be even worse. Why is this a problem? Where this node can actually swing a very large voltage. You can have on the order of VDD kind of swings at this node. And so the power loss, because of the large voltage swing, the power loss on this bottom plate parasitic could substantially DQ your circuit. Okay? So of course the solution is very simple. Just use two capacitors. I'll draw them like this to emphasize the bottom plate. And now, because of the fact that this is a fully balanced circuit, this bottom plate is a virtual ground. In other words, this AC-wise, this node doesn't move, and therefore any parasitics at this node are negligible. So that's really nice. Okay. Let's say to keep the tank clean. Yes?
Well, if we put two capacitors parallel to each other, are they the same?
Yeah, you could do that as well. For instance, I could have structure like this, right? But then you still get the bottom plate, right? So you still would have your bottom plate on both sides now. And preserve symmetry, but you still get the loss. Okay. In fact, this is nicer because you just split the capacitor in half. Here you actually have to use twice the capacitance, so you do pay a penalty for doing that. Okay, let me say also a few words about, so this is pretty much the topology of choice. If you look at papers or products, and if you could actually peek inside and look how they implement their oscillators, they're usually differential oscillators. If they're MOS, they're implemented either like this or something like this. Actually more like this. And if it's bipolar, instead of having a direct cross-coupling, you'd have a capacitive feedback. That's because in a MOS amplifier is much more linear, and so you can have very large voltage swings here and still not compress this device. In a bipolar amplifier, we know a differential pair has a linear swing of around, 120 millivolts or so. So if the differential swings bigger than a couple hundred millivolts, it drives this device into deep compression, and the oscillation amplitude would basically stop. So in order to get a larger oscillation amplitude, I would divide the output before I apply it to the circuit. So that's the reason why we use that cap feedback. Actually, that's probably worth writing down. So in fact, I think it was David who pointed this out a few lectures back. So if we compare the nonlinearity, the negative resistance of a MOS versus a BJT differential pair, it might be something like this. So this is the minus conductance of the device versus the oscillation amplitude. And so you can see that this device compresses very quickly and would result in a very small output amplitude. Let's say on the order of a couple hundred millivolts, whereas this guy can swing almost to VDD. So here's the picture. let's say I use a PMOS version, have my tank, and basically something like this. Okay. If I use bipolar, the way to get larger swings, and as I mentioned earlier, swing is important for phase noise. What I do is instead of applying a direct feedback, I use a cap divider. So let me draw this a little bit better here. And there's also some intrinsic cap here. If not, you can add some. And now the voltage swing here, the large swing here, can be much larger than the internal swing. Should have drawn this as a diff pair, actually. It's more clear. So now you can see that this swing can be much larger than the differential input swing. Okay? And you guys all have the necessary tools to analyze these differential pair oscillators because you spent a lot of time analyzing differential pair Gilbert cell mixers. And basically, you have curves like this, which is a normalized harmonic currents of, let's say, a diff pair, differential BJT diff pair, versus B, the overdrive voltage. And you can generate similar curves from MOSFET devices. Interesting point is that these curves are compressive. And that's because naturally a BJT will compress, right? Because the current is fixed. The sum of the currents has to equal to the bias current. So you don't have to do anything special for a bipolar or a MOS differential pair to compress. Whereas with the bipolar device, we noted that if you build an oscillator from a single transistor, it won't compress unless we limit its current. Okay? So that's an important difference between differential oscillators and single-ended oscillators. All right, questions? Yes, Lee.
What's the difference between having a current source and just ground it?
Yeah, it's also a very good question. So if you don't ground it, it's exactly what I was talking about. If you don't have a current source, there's nothing limiting the current, right? And so it self-biases. There's a couple of problems with that. First, it's a little bit dangerous because that operating point is going to vary over process and temperature. You'd much prefer to establish, actually the way you'd do it would be like this. You'd much prefer to establish the bias point through this current source, which is fixed, and it's basically fixed with some reference voltage somewhere in the circuit. And then you can have a very good prediction of what the oscillation amplitude is going to be. If you don't do that, then this self-biases, and you have to make sure that over all corners it self-biases with enough loop gain to oscillate. The other difference is the limiting mechanism. The limiting mechanism is likely to be close to triode region. So the oscillation amplitude is going to get big enough, push these devices into triode where the loop gain will drop, and that will establish your oscillation amplitude. That means actually the advantage is you can swing rail to rail. Okay?
Won't you also be more linear if you don't put a current source? The overall transfer function of this cell would be more linear.
Yeah, and that's exactly why you end up going to VDD, right? It's the triode region that ends up limiting you. Yeah, but remember, linearity doesn't really matter so much for an oscillator, right? I'm sorry? Yeah. Okay. Now, actually something interesting to make you guys think a little bit. You know, we're calling this thing an oscillator, but boy, it also looks like a mixer, right? I have a diff pair here. I have a current source. I can think of this current source as a noisy current source. That means it has RF current. And this is a switching pair, right? And there's an LO signal. What's the LO signal? Well, it's driving itself. So it's a self-oscillating mixer. And so then you can see that the noise at different harmonics of basically the switching frequency can fold into band due to the switching mixing action. So the noise of this circuit is also complicated, just like the noise of a mixer is complicated. All right, just to get you guys thinking a little bit ahead. Okay, good questions, guys. Any others? All right, so let's say a few more words about VCOs. Okay, and I already introduced the concept of a VCO. A VCO is basically either a current or voltage controlled oscillator. Usually for RF frequencies, it's a voltage controlled oscillator. And the idea is that I have some control voltage that can change the output voltage. So if I were to plot frequency versus control voltage, it might look something like this. I might be able to go from some frequency F max to F min. Okay? And the reason I need a VCO is that if I'm building a receiver, let's say a very simple receiver, I want to use a fixed IF frequency, let's say, to do some filtering. And that means that my LO should be RF plus or minus IF. And if my RF frequency changes, right, if I have multiple channels, then my LO frequency should also change to select the right channel. So, for instance, if I'm doing a frequency division multiple access, that means I'll have a bunch of RF channels, channel 1, 2, 3, dot, 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 let's say 50. And at any given time, I may be on any one of these channels. And so that means that I need to be able to change my LO frequency. And so somehow I'm going to find the right control voltage to pick the right output frequency. And in an ideal world, this curve would be really linear, and it would be very predictable. And so I could just, in some ROM, store the right value of control voltage to hit every output frequency. But unfortunately, we don't live in an ideal world. We live in the real world, where you can imagine that this curve is a kind of a nasty shape, and it varies all over the map over process and temperature, right? So over temperature, it may have a smaller range or a larger range, and over process, it has basically something like that. So how we actually determine the control voltage to hit a precise frequency is the subject of another lecture. That's how we build synthesizers. They synthesize precise frequencies based on a reference. But from today's perspective, today's lecture's perspective, we want to find out how we can vary this output frequency. Okay, so last lecture we talked about using varactors, PN junctions, to vary this frequency. It's a very simple concept. So here, let's just draw it. So I have my tank, and let's say I connect a diode like this. And I also might have some fixed capacitance. This might be 2 series caps, as we talked about before. And then I'm going to basically call this the control node. And if you're really antsy about the fact that this is a floating node here, you could also put, let's say, some resistors to ground. So basically, this is a large resistor to ground. To set the DC equal to 0 volts. Okay? And this is also a large resistor. And the idea is that I'm going to change this control voltage, and in such a manner, well, actually, this should go to VDD in this case. So if I go to VDD, then the forward bias is equal to 0. If I go to 0, I have maximum reverse bias or minimum capacitance. So I can vary the capacitance of these diodes by changing the bias here. Okay? So this, using PN junction diodes is one way to go. In last lecture, we talked about the parasitics of a PN junction diode. And again, we can see the advantage of hooking them up in the right way so that the parasitics end up at the virtual ground. So if I draw, let's say, in a P substrate, I might have a N well and an N plus contact and a P plus contact. So this is my P junction, this is my N. And so really the actual diode is very tiny. It's between here and here. That doesn't look so good. But the actual diode happens, there's a depletion region around here. And then there's some resistance. So unfortunately this diode has some series resistance. It has a finite value of Q. So the equivalent circuit looks like this. And that's why I've actually put 2 N plus contacts around it to reduce this resistance. In fact, what would be better is if I actually put a ring around it. So from a top view, this would be the P plus, this would be the N plus, okay, to try to minimize that resistance. And you can see that the N node here is dirty because the N node has this well capacitance to substrate. And so what I'd like to do is put the N point at the virtual ground, right? And then that changes the way you would bias this. We talked about this already, so I won't go into the details. I think you guys remember. All I have to do is now ground this side and connect this to VC, and I can have a nice varactor controlled. Now, if you plot the typical junction capacitance normalized to zero bias capacitance versus control voltage, so let's say this is 0, the curves look something like this. It's a very gradual change, and the slope depends a lot on the junction profile. Okay, so most of you guys are familiar with n equals 1/2. N equals 1/2 is an abrupt junction. In other words, we assume that you have P doping on one side and then N doping on the other, and it's a step function change. Now, it's pretty hard to build step functions in real life. It's much more likely that there's going to be some kind of actual gradient, right? Not an infinite gradient. And that gradient will lead to a different kind of slope. And that's why in SPICE, N is never equal to 1/2. It's always something like 0.3 or 0.4. In fact, if you do N equals 1/3, that corresponds to a linear grade. In other words, the doping changes linearly from one side of the junction to the other. As we'll see later on, if you had N equal to 2, then you would have a linear relationship between frequency and control voltage, frequency of oscillation and control voltage. That's because the frequency of oscillation goes like square root of C, right? So square root of square gives us linear. But that's not very practical for most kinds of junctions we build. It's mostly these kinds of junctions that are practical. And if you look at how much variation in capacitance you get, let's say even with N equals 1/2, I did a simulation or a simple calculation, and I saw that I could change the capacitance by something like 60%, going from 0 volts to, let's say, minus 3 volts, reverse bias. So this is the reverse bias. Okay? And so that's pretty good, but remember, the frequency is square root of that. So if I get 60% capacitance change, that's only 30% frequency change. So, and again, I'm making some very optimistic assumptions. So if you go back to what people did in the old days, if they needed more frequency tuning range, if they needed 100% or 50%, what they would do is use even higher voltages, and voltages that were even higher than you were allowed to put in the process. And the way they did that was they would have a charge pump circuit somewhere generating a high voltage, and they'd use that voltage only to touch the control node and vary the capacitance. Okay, obviously that's really inconvenient. If you can avoid doing that, you'd like to avoid it. So one way to avoid this is, instead of using a PN junction diode, so this is a diode characteristics, is to use a MOS diode. So MOS capacitor structure as you guys all know from 105 and 130, looks something like this. Basically, I'm going to tie my source and drain together, and let's say I ground it, and let's say that this is P sub, and so this is N plus, this is N plus, and then I have my gate here. I know that the capacitance of this structure varies depending on what region I operate this device. So first of all, if I put a positive voltage, let's start out with a negative voltage. No, let's do a positive voltage. Okay, so let's say I use a positive voltage here. Okay, what happens if I put a positive voltage here? Actually, no, I want the negative voltage. Okay, if I put a negative voltage here, then that's going to attract holes to the surface, right? And there's plenty of holes in this P substrate, right? So we call this accumulation mode. In other words, we accumulate holes at the surface, and the capacitance of this structure looks very much like the capacitance of a parallel plate capacitor, where this is the first plate and the bottom plate is actually the substrate. Okay? Now, in the other extreme, if I put a large positive voltage, then we know that we form an inversion layer. So electrons accumulate at the surface. Or in other words, we get the inversion. Inversion because the p-type material inverts to an n-type material at the surface because I pull the surface potential high enough to cause that to happen. And again, this looks a lot like a linear capacitor. Okay? Now there's an issue here with frequency because even though there's lots of holes around, electrons are only generated thermally. So if these contacts are far away, this wouldn't be a very good high frequency capacitor. But since I have contacts that are close by and they actually form a continuous channel here, there's plenty of electrons that can come in and form a capacitor. Okay? So the capacitance in this region is roughly Cox, right? Where Cox is WL epsilon over Tox. And the capacitance here is apparently also Cox. Now, if you really want to get complicated, you could say, well, quantum mechanics says that charge doesn't quite accumulate at the surface. It's far away from the surface. Not that far away, but effectively, Tox just gets modified. And it gets complicated because depending on the voltage you put here, the Tox will vary. We'll come back to that point. But first order model is that the capacitance is just Cox, right? So that's not very interesting. What's interesting is if I put an intermediate voltage on here. So let's see what happens. Okay. So first of all, let's plot what you guys all know. Let's plot the Moss-Varactor curve. I've observed that for large negative voltages, it's Cox, and for large positive voltages, it's also Cox. And what I find is that in a simple model, in this region, we call depletion. This is before a channel has formed. So in this very simple model, we assume that at the VT of the device, the threshold voltage, almost instantaneously a channel forms and we get this Cox capacitance. Of course, this is not physical. We'll come back to that. We're also assuming that Cox is constant. We'll come back and look at that. Out here in accumulation, we assume that the capacitance is Cox. We know that the flat band voltage corresponds to the point where the device actually has zero fields in it. If we go beyond flat band, what happens is that we have basically two capacitors in series. So I have Tox, and then I have this depletion region. Let's call this T-dep. And the effective capacitance looks like the series combination of Cox and C depletion. And C depletion is, of course, epsilon silicon divided by X dep, where X dep is the depletion region depth. And you guys know that X depletion, you can calculate how the depletion region varies with the voltage drop across here, and that leads to this curve here. Okay? Now, Yes.
So in all this, you've got the bulk connected to the drain source, correct?
Yes. Yeah. So let me draw a better picture to make that clear. So this is my P sub. I'm going to build a capacitor like this. So this is the gate, this is the bulk, and I'm going to ground these guys so that I have a source for the electrons at high frequency. Okay? And so the capacitance is between gate and bulk, right? So if we actually come back and look at a real device, well, first of all, this is great because in this region, the capacitance varies a considerable amount. We go from Cox to the minimum capacitance, which is Cox divided in series with the small capacitance. So this small capacitance will dominate. And this range can be tremendous. It can be a factor of 2 or 3 or even 10, depending on how close you want to push into this region. So you have this very large capacitance ratio, which means that in theory, you could have a very large frequency tuning range. Okay? Now, this curve, of course, doesn't look like this. In real life, you don't invert instantaneously. Inversion starts somewhere here in subthreshold, and so this curve actually is much smoother. And also, because of the quantum effect and because of polydepletion, as you hit higher and higher gate voltages, the effective oxide gets smaller and smaller, larger and larger, because of, let's just consider depletion region. So depletion region, this is due to polydepletion, because you start forming a depletion region in your polysilicon gate. You don't have a metal gate. Doesn't really matter though, because now I can use a variable capacitor either in this region or in this region, and I can get a very good range. Typically this transition, I didn't do a good job drawing it, but this transition is sharper than this transition. So if I want to maximize the frequency, the voltage range, I would prefer this transition. And you might say, well, why do you want to do that? The reason is that if that transition is very sharp, then just even without doing any kind of analysis, you can convince yourself that any noise on this node is going to cause the capacitance to change, which is going to cause the frequency to change. So if this transition were only 10 millivolts, you could see that a 1 millivolt noise signal on this node, the control node, would have a huge impact on the oscillation frequency. Well, that's not good. So we'd like to actually maximize the range, the voltage range, to minimize the impact of noise coupling to the oscillator. Well, if you basically think about the Q of this structure, if you're in inversion mode, then the quality factor, so let's say that this is also grounded, so this is a capacitance to ground, then in inversion mode, you'd form a channel here, and the electrons basically would flow to ground through here. And so basically the resistance of this channel would determine the Q of this capacitor. Okay? On the other hand, if you do accumulation mode here, then there would be holes, and the holes actually have lower mobility. So holes have roughly 2x lower mobility, and so the Q would be roughly 2x lower. So definitely we'd like to use electrons. And so we have a choice. We could either use inversion mode N-type, or we can use accumulation mode N-type. So what would the accumulation mode N-type look like? So this would be a accumulation mode MOS varactor. Basically, you might think just build a PMOS device. So we have an N-well, and I'm going to put a gate voltage here. And I want electrons to come to the surface, so I put a positive gate voltage. and that would accumulate electrons basically at the surface. And that's great. Electrons have good mobility. And the other terminal I would form by making a bulk contact. So I would put an N+ region here. And actually, doing this has another benefit. The benefit is that this thing at high frequencies will not invert. Okay, why is that? Yeah, the electrons are thermally generated. So, excuse me, the holes here are thermally generated. So to get holes, to get inversion, you need holes here. And holes, the thermal generation process is pretty slow. Last time we made that fast by putting P+ contacts here, right? That's how we build a transistor. But we get rid of those P+ contacts and just use a bulk connection. And now we can actually get a device whose curve looks something like this. So this is the flat band voltage, this is Cox, and basically inversion does not happen. And that's nice because that means that the capacitance is monotonic versus control voltage. So I can go from 0 all the way to flat band and get a nice monotonic response. Okay? Questions? Comments?
Can you comment on the choice of W over L on the effect of the choice on the Q?
Yeah, so clearly you want to make L as small as possible because that means that your resistance, channel resistance, is minimized. But if you use an L min, the layout may become awkward. You might have to have a very large W. So if the Q is already high enough that you can afford to use a larger value of L, you can do it because of course the total capacitance is Cox times W times L. So basically you pick L small enough to get sufficient Q. And the reason that I say sufficient Q is remember that you're building a tank. So in a tank you have inductor, you have a capacitor. This is L, this is R, let's say L, this is C, this is RC. We can convert this into a parallel LCR circuit. This is RLP, this is RCP, and the quality and the value is going to be Q squared times the series resistance roughly. And the value, the quality factor of inductors is, let's say, 5 to 10 in a typical process. That's a CMOS process. Say RF frequencies around 1 to 5 gigahertz. You'll find that the varactor Q actually is much better. So QC, CV, let's say, call it a varactor, depending on the process, it may be anywhere from 20 to 30. So much better. And so you actually don't, because you're really limited by this inductor anyway, right? So the overall Q is QL in parallel with QC. If QL is much larger than QC, it will dominate. So you may be able to afford to only have a Q of, let's say, 15 on the varactor and still have a good tank. And so then you would choose an L basically as large enough to hit that quality factor, and that would minimize the layout area. Okay? Or make the layout area less awkward, let's say. Okay, so last topic for today, we'll talk about something that's become very popular, and that's switch capacitor varactors. And the idea of a switch capacitor varactor is that instead of hitting the whole tuning range with, let me draw it with ideal switches first. Instead of hitting the entire tuning range with just one varactor, let me try to hit the tuning range with a bank of capacitors and let's say one varactor. So this is a linear varactor. And then these are basically binary weighted capacitors. So let's say this is CA, this is 2CA, this is 4CA. Actually, I should have do it the other way. CA, 2CA, 4VA, and this is 2 to the N times CA. and I can just ground these, for instance. Or I could have a differential version. So by turning on and off different switches here, I have a coarse tuning. And I have a fine tuning. Now, in Al's project, he talked about something similar to this, except he got rid of the fine tuning. He was able to hit he was able to get enough frequency resolution just using the digital tuning mechanism. But you have this flexibility. You can actually use both. What's interesting is you might think, well, you know, why is this a new idea? By new, I mean the past 5 or 6 years, maybe a little bit more. The reason is that these resistors have to have very low on resistance. So for high Q, need low on resistance. And the on resistance, basically in triode region, the current is approximately mu C ox W over L, VGS minus VT times VDS minus VDS squared over 2. So if I take a derivative of that with respect to VDS, that gives me my conductance. So switch conductance, the on conductance, and let me evaluate it at VDS equal to 0, and that gives me simply mu C ox W over L VGS minus VT. Okay, so with process scaling, by making L smaller and smaller, I'm able to make this switch more and more conductive. And there was kind of historically a turning point somewhere around, let's say, 0.35 micron, where the switch on resistance with a reasonable switch size, and I'll talk about what I mean by reasonable switch size, was low enough that it wouldn't DQ your tank. You can get basically, if you built a cap like this with a MOS device, then the on resistance would give you Qs, let's say, on the order of 20 or so, 15, 20. And so this is process dependent, because as process scales, basically Cox gets bigger, right? Because Tox is getting smaller. Mu is roughly constant, maybe going a little bit down with process, but L is also shrinking. So the net benefit is a huge increase, because this is epsilon ox over Tox. So the product of Tox and L helps you get lower and lower resistances. Okay. Now you might say, big deal, just make the device bigger, right? Make W huge, right? So why not just make a huge device, right? Well, the reason is that this device has parasitics. So there's C drain to bulk parasitics here. When I turn this off, let's say I ground this node. And there's also this big overlap capacitance. And so it's kind of hard to turn this capacitor off. I can turn it on, right? But I can't turn it off, because these bulk capacitors, these parasitic capacitors, should be much smaller than this capacitor. Otherwise, the circuit doesn't work. Okay? Now, Al showed you guys another idea, which is clever. Instead of using a switch capacitor, just use a MOS device and switch basically use the body voltage to switch its capacitance. So I could have a binary array of MOS devices, and I use this body voltage basically to either switch this into accumulation or into deep depletion, and that would change its capacitance. So what's important is Cmax to Cmin. The maximum capacitance, which is Cox, and the minimum capacitance, which is determined by depletion. Here, Cmin is determined by a series combination of this guy and these parasitic capacitors. Okay. The other neat thing, which there's no time to show you guys, but you can see pretty clearly, is that I can actually scale these devices so that they have constant Q. In other words, if I double the capacitance, then I can actually live with double the parasitic. So I double the size of the switch. That doubles its conductance, so the net Q remains the same. So if I just design a unit cell element and scale it, the overall Q is really determined by the quality factor of one unit cell. Okay? All right, I think we'll stop there and have a nice Thanksgiving, guys.